Good morning, students. Today starts with the topic nuclear energy. Right. So, as already we discussed, the relation of binding energy per nuclear to the mass number A. That means specific binding energy to the mass number A. We have the graph like this, right? So in this we study the mass number here from A to, that is A30 to A170 has the constant specific binding energy per nucleus. Specific binding energy is constant, so that value is almost approximately equals to 8 mega electron volt. That means, so from here to here the value is almost constant, so that value is 8 mega electron volt, right? So the mass number which is less than 30 here, from here to here, the mass number A which is less than 30 has the lowest specific binding energy, right? Then the mass number which is greater than 170 as also the less binding energy. That means here almost the values reaches to 7.5 or 7.8 mega electron volt. Right? So compared to this value, the specific binding energy here the values decreases. Right? So the mass number which lie between A30 to A170. So all the nuclei are stable here. So the nuclei which lies between 30 and 170, those are highly stable in nature, right? So here the mass number which is less than 30, the possible of the nucleus which are less than 30 has to reach the stable by joining the nuclei. That means combining two nuclei, then it goes to the stable nuclei, right? So two lighter nuclei, right? So this is one lighter nuclei and this one is another lighter nuclei. That means the nuclei which is less than 30, right? So those we call as lighter nuclei. These lighter nuclei fuse together, that means combine together to form the nuclei of heavier mass. That one we call heavier nuclei, right? So heavier nucleus, this will falls in the region between 30 and 170. Then this attains the stable nuclei, right? So during this process, the energy is released. Right? So the lighter nuclei can attain the stable nuclei by fusing with the another lighter nuclei. That means two lighter nuclei fuse together to form a heavier nucleus. So this nucleus will be stable, right? So during this process, the energy is released, right? So next, in the similar case, here we have the heavier nuclei. That is the mass number which is greater than 170, those are all heavier nucleus. So as in the heavier nucleus, the binding energy per nucleon is less, right? So as binding energy per nucleon is less, that means this value is comparatively less than that of the 8 mega electron volt. That means here the binding energy of the nucleus is more. That means EB is more. So there is difference in binding energy per nucleon to the binding energy, right? So in the second case, EBN is less, comparatively less. That means almost less than 8 mega electron volt, right? So here the binding energy is more in the nucleus. As the binding energy is more, then the mass is less. So as mass is less, the nucleus which having the mass is able to divide into fragments of the similar nuclei. It can divide into two nuclei of the lighter nuclei. So this will comes under the region of the stable, right? So this one is the heavier nucleus. So this nucleus is able to split into two separate nuclei, that is of the stable nucleus, and here also stable nucleus of almost same mass, comparable mass, right? For example, if we have the mass of heavier nuclei is 2, then this nuclei splits into the masses of two same, that is 120 and 120, right? So as 120 is lies between 30 and 170, this nucleus will be stable. So during this process also the energy is released, right? So in these two processes the energy is released. So here the fusing of two lighter nuclei to form the heavier nucleus, then this process is called as fusion, right? Then here the splitting of heavier nuclei into lighter nuclei, so this process is called as fission, right? So in these two process, in fusion and also in fission, the energy release is common, right? So that energy we call as nuclear energy, right? So what is nuclear energy? The energy which is released during the nuclear fission or nuclear fission process, then that energy we call as nuclear energy, right? So this one we call as fusion or nuclear fusion. So this one fission or nuclear fission, right? So the main important is binding energy per nucleon is constant in between the region of A, that is mass number 30 to mass number 170. So for lighter nuclei, the region which less than 30, so these are lighter nuclei. So these nuclei will attain the stable nuclei by combining with the other lighter nuclei, right? So if these two lighter nuclei combine to form a heavier nucleus, so this nucleus will be unstable, right? So during this process the energy is released, right? So that energy we call as nuclear energy. So similarly, the heavier nucleus has the binding energies, that is comparatively less than that of 8 mega electron volt, though here the mass is less, that is the nucleus is loosely bounded, hence it breaks up into two separate nucleus of comparable masses, right? So during this process also the energy is released, so that energy we call as nuclear energy, right? So and the process of combining the two lighter nuclei fuses together to form a heavier nucleus, that time the energy is released. That process we call as nuclear fusion. That means fusion means combining of two lighter nuclei, right? So next, the splitting of heavier nucleus into two separate nucleus of comparable masses, that time also the energy is released. So that process we call as nuclear fission, right? So here if we write the definition of the nuclear energy, the energy is released during the energy is released during nuclear fission or fusion process, and that energy we call as nuclear energy, right? So what is nuclear energy means? The energy which is released during the combination of, that means combining of two lighter nuclei or the splitting of heavier nuclei into two nuclei of comparable masses, then that energy we call as nuclear energy, right? So next we will discuss starts with the nuclear fission. So what is nuclear fission, and we will see few examples on the nuclear fission, right? Next is into fragment of nucleus of comparable masses and releasing of 2 to 3 neutrons and energy, right? So this process we call as nuclear fission, right? So what is nuclear fission? So it is the process in which splitting of the heavy nucleus into fragments of the nucleus, that means it splits into two nucleus of comparable masses and releasing of 2 to 3 neutrons along with the energy, right? So this process we call as nuclear fission, right? So for this we have one example, that is bombarding of the uranium isotope with the neutron, right? Bombarding is nothing but hitting of the bombarding of uranium isotope with neutron. So when the uranium isotope 235 U 92. So here the mass number is 235 and uranium 92 is the atomic number, right? So with the neutron, right? So if you write the reaction for that, uranium 235 and here it is 92 bombarded with the neutron, right? So here we getting uranium 236 and here it is 92, right? So now this uranium is splits into fragments of the nucleus, that is of the comparable masses, right? So that one is converted into beryllium of 144 and krypton of 59 plus here it emits 3 neutrons. Right. So this one is the example for the nuclear fission. So this one is the uranium isotope, that is uranium 235, right? So when uranium isotope 235 is bombarded with the neutron, so bombarded with one neutron, we get the heavier nucleus of 236. Mass number is 236. That means this one value is greater than 170. So this nucleus is heavier nucleus. So this nucleus splits into two separate nucleus. So one is beryllium of 144, that is mass number is 144, it lies between 30 and 170, right? So here 89, that is krypton 89. So this 89 is also lies between 30 and 170. Then these two are stable nucleus, right? So along with this, three neutrons are releasing along with that energy, right? So here 2 to 3 neutrons are released, right? So this one is one example. So similarly, we get for the same reaction, that means same, the uranium bombarded with the neutron, we get different elements of different mass numbers, right? So if we take one more example, uranium 235 92 plus 1 neutron, we get 236 uranium 92. So the second example is 140 xenon plus 94 is for here it releasing two neutrons. So 140 plus 94 plus two neutrons, right? It is 54. Here is 38. Right? So these are the two examples. So this one is example 1 and here this one is example 2. So here we have the same mass, that is atomic mass and the neutron. So here the end products are different, right? So these are called the fragments, right? So the energy which is released during this process, that is in the nuclear fission process, the energy which is released, that energy is used as the kinetic energy of these fragments plus along with the kinetic energy of the neutron, right? So the energy which is released during this process, that is the splitting of the uranium into its constituent nucleus, then that energy is utilized as the kinetic energy of these fragments and the kinetic energy of the neutron, right? So that kinetic energy, the neutrons are very fast moving neutrons, so that means it has the energy of the almost 2 mega electron volt, right? So the energy of the neutron is almost has the value that is 2 mega electron volt, right? So this is the nuclear fusion, that is definition plus along with the example, right? So here we have two examples. One, we get the end product of the nucleus Ba and Kr, and one is Xe and Sr. So here three neutrons are released and here two neutrons are released, right? So these fragments of the nucleus, so these are almost radioactive elements. So these elements are radioactive elements. Then these radioactive elements undergoes beta decay. Then it emits the beta radiation. That is, it emits the electrons or positrons. Then later it gets the stable nuclei. Right. So these end products, that is, these fragments are radioactive in nature, right? So for that reason this undergoes beta decay, then it attains the stability of this nucleus, right? So next, so this is about the nuclear fission. So we have the nuclear reactor. So this is for the long answer. So once they ask about this one. So nuclear reactor. So what is nuclear reactor? So nuclear reactor is a device in which controlled fusion reaction takes place. So that one we call as nuclear reactor. So from this we utilize the energy that is emerging out from the fusion process, that is emerging from the fission process, that is used to obtain the electricity, right? So what is nuclear reactor? So nuclear reactor is a device that is used to obtain the electricity, right? So nuclear reactor, it is a device in which controlled nuclear fission takes place. Chain reaction takes place. Right? So nuclear reactor. So what is nuclear reactor? Nuclear reactor is a device. So it is one device. So in this device, what happens? That is controlled nuclear fusion process. That means splitting of the heavier nucleus into its fragments. That is by releasing the energy along with the neutrons. Right. So that one we call as nuclear fusion. So then here, what is the meaning of the controlled nuclear fusion, right? So in fusion process we have two reactions, that is one is controlled nuclear fission and another one is uncontrolled nuclear fission, right? So the meaning of the nuclear fission we know, that is the splitting of the heavier nuclei. So this one is the heavier nuclei. So this nuclei is splitting into two separate nuclei along with the neutrons are released. Along with this neutrons are released. So this process we call as the nuclear fission, right? So if we consider this one as uranium, right? So in the previous example also we taken. So this uranium is splits into two nucleus, right? So here we taken this one as Da and Ka, right? So these are the two nucleus. When this uranium is bombarded with the neutron, right? When one neutron bombarded with this uranium, so this uranium is splits into two nucleus along with the emission of the two neutrons, two or three neutrons here. 2 to 3 neutrons are releasing, right? So this one is the nuclear fission, right? So here what is controlled nuclear fission? So controlled nuclear fission means when this neutron is bombarded with the uranium, so here we are obtaining this nucleus, so only concentrate on the neutrons, right? So when neutron bombarded with the uranium, so here we are getting 3 neutrons, 3 to 2 neutrons, right? So these are the neutrons, right? So further in the sample we have many number of the nucleus, right? So again this neutron has to bombarded with the same uranium nucleus, right? So once again it emits 3 neutrons, right? So this process is the chain process, right? So here also this neutron bombarded with the uranium nucleus, again here we are obtaining the 3 neutrons. So here the third neutron bombarded with the uranium nucleus, so again here we are getting 3 neutrons, right? So once these neutrons are released So these neutrons have the energy of almost 2 mega electron volt. So each neutron having 2 mega electron volt. So as this chain reaction continues, so this energy goes on increasing. Right? So here we have 1, 2, 3. That means the total energy released here is 6 mega electron volt. Right? So similarly here the number of the neutrons here is 9. That is here we getting 18 mega electron volt. As this continues, the chain reaction goes on continuing. That means the energy release is increasing. Right? So this we cannot control, means that one the releasing of the energy is more and it results to the explode of the reactor, right? So for that here when neutron bombarded with the uranium, so here the possibility of the emission of 2 to 3 neutrons are emitted. From these 3 neutrons, 2 neutrons are made to observe. Right? So these 2 neutrons are made to observe, then only 1 neutron made to bombarded with the nucleus of the uranium. Right? So then these will not possible here. Right? So again here this will not possible. Right? So as the 2 neutrons are getting absorbed, that means these 2 neutrons are controlled. So only 1 neutron are made to incident with the bombarded with the uranium. So again here we are getting 3 neutrons. So these 3 neutrons, in this again 2 neutrons are going to absorbing by using the control rods. So control rods are used to absorb these neutrons, right? So these are absorbed, right? So only 1 neutron are made to bombarded with the nucleus. Again it will bombarded with the nucleus of the uranium. Again here we are getting 3 neutrons, means here 2 neutrons are getting absorbed. So that process we call as controlled nuclear reaction. Right? So if we control this nuclear reaction, then the energy which is released is used to electricity. Right? So that is the meaning of the controlled chain reaction. So this one is the chain reaction. When 1 neutron bombarded with the uranium, we are getting 3 neutrons, right? So these 3 neutrons bombarded with the uranium, again we are getting 9 neutrons. That means the number of the neutrons goes on increasing. That means that one is the chain reaction. So that process is the chain reaction. So we need to control the chain reaction by using the control rods. These control rods are absorbing neutrons, that is excess of the neutrons, then made only 1 neutron to bombard with the uranium nucleus or heavier nucleus. So here we have taken uranium, right? So that's why this bombarded with the uranium nucleus, right? So this process is called the controlled nuclear fusion, right? So if we are not using this controlled rods, then it goes on increasing the number of neutrons and the maximum energy is released. So that one we use as atom bombs. So this uncontrolled nuclear fission process is used in the atom bombs, or we call that one as the nuclear bombs. Right? So this one nuclear bombs. So in nuclear bombs, uncontrolled nuclear fission takes place. So for obtaining the electricity, controlled nuclear reaction, that is nuclear fission, takes place. That is the difference between the controlled and uncontrolled, right? So in nuclear reactor, controlled nuclear fission takes place, right? So you understand this one. Here we are understand the chain reaction along with this controlled and uncontrolled. So controlled reaction means we are observing the neutrons which are released from the uranium, right? So bombarded of the uranium with the neutron, then excess of the neutrons are observed by the controlled rods, then that reaction we call as controlled nuclear fission reaction, right? So next, the nuclear reactor. if you write the block diagram of the nuclear reactor, so this one is the core. So this core is surrounded by the reflector. Right? So this core is connected with the coolant and it connected to the heat exchanger. So these two are the control rods. So this one is the heat exchanger. So this one is the heat exchanger or steam generator. So this one is steam supplied to turbines. Here this one is water supplied from condenser. So this one is the block diagram of the nuclear reactor, right? So in the nuclear reactor, it consists of core. Then this core is surrounded by the reflector, and this core is connected with the control rods. So here any number of the control rods. Here we need only two control rods, right? So next, this heat is released during this nuclear reaction. That one is ejected out from the coolant. That this coolant is supplied to the heat exchanger. Then in the heat exchanger, water supplied from the condenser is passed into the heat exchanger, and here the heat which carried by the coolant converts that water into the steam, right? So that steam is supplied to the turbines. From the turbines, by rotating the turbines, we are generating the electricity, right? So this one is the block diagram of nuclear reactor. Right. So the core consists of the first point here. The core consists of the nuclear fuel, right? So this core is consists of the nuclear fuel. That means nuclear fuel nothing but fusionable material. Fuel is nothing but the fusionable material. That means the heavier nuclear. So here in the nuclear reactor we are using uranium 235 and or plutonium, either any one. Right. So the first is the nuclear fuel. So nuclear fuel is kept inside the core. So here we are getting the nuclear fuel. That means the fissionable material which is placed inside the nucleus. Inside the core. That is the fissionable material. Either we are using the uranium 235 or plutonium 239. Right. So these are placed inside the long cylindrical aluminum tubes. So these are placed inside the long aluminum tubes, and that one is covered with the graphite core, right? So this one is covered with the graphite core, right? So this one is about the nuclear fuel. So what is nuclear fuel? Nuclear fuel is nothing but the fissionable material. So fissionable material is the heavier nucleus. So here in nuclear reactor we are using the uranium or plutonium as the nuclear fuel, right? So this nuclear fuel are molded in a long cylindrical aluminum tubes, and that one is placed with the inside the graphite core, right? So this core is made up of the graphite, right? So next, after nuclear fuel, the second one is the reflector. So what is reflector, right? So when this uranium is bombarded with the neutron, then the neutrons are emitted. That means it releases the neutrons, that is 2 to 3 neutrons, and it goes on continuing. Those emitted neutrons again is bombarded with the nucleus, again the neutrons are emitted. That means the chain reaction is takes place. So that chain reaction, in that chain reaction the number of the neutrons which are emitted or possibility of escaping from this core to the outside, right? So those neutrons are sent back to the core by the help of the reflector. That means the escaping of the neutrons are made to send back to the core with the help of the reflector, right? So what is the need of the reflector? Means it helps to send back the neutron inside the nucleus. That means the escaping of the neutrons is avoided by the reflector, right? So that's why the reflector we are using outside the core, right? So the core is covered by the reflector, and it helps to, that is helps to send back the neutron into the core, right? That means the escaping of the neutrons are avoided by the reflector, right? So the reflector helps to, it helps in send back the escaping neutron into nuclear reactor or into the core. So from this leakage of the neutron is reduces. That is leakage of neutron reduces. That means it reflect back to the core. That one is the help of the reflector, right? So the first is core. The core is consists of the nuclear fuel, that is fissionable material. So this core is covered by the reflector. During nuclear fusion process, the number of the electrons are releasing. So those electrons are possibility to escape out from the core. So those escaping neutrons are sent back to the core with the help of the reflector, right? So these are the two. The first is nuclear fuel and second is the reflector. So the next, the third point is moderator. So the next third one is moderator. So what is the help of the moderator, right? So here, as already said, the uranium nucleus is bombarded with the neutron, then the electrons, sorry, the neutrons are released along with the energy, right? So these neutrons are made to bombard. So here we are obtaining three neutrons, right? So three neutrons are again made to bombard with the uranium, right? So this uranium, that is chain reaction, to take place this chain reaction, right? So in the first process, when one neutron is bombarded with the uranium nucleus, we are obtaining the three neutrons. These three neutrons having the highest energy. That means it has the energy of 2 mega electron volt. That means these neutrons are very fast moving neutrons, right? So these are very fast moving neutrons. So these neutrons, fast moving neutrons, has to collide with the uranium nucleus. That means when these fast moving neutrons bombarded with the uranium, then this neutron is penetrating from the uranium, right? So here we need to, as we observed in the last relation, that is N10 is bombarded with the uranium 235 and its atomic number is 92. When this neutron is bombarded with the uranium, first we get uranium 236 92. That means this neutron is getting inside that of the nucleus of the uranium, right? So that means its mass number is increases, that is 236. So here, as this neutron is very fast moving, we need to place this neutron inside the nucleus, right? So because of this fast moving neutron, this neutron is not be placed inside the nucleus, it is penetrating and goes out of this nucleus. So here there will be no possibility of the nuclear reaction. That means we need to place this neutron inside the nucleus of the uranium, but here the neutron is very fast moving, so this neutron is penetrating from the nucleus, so there is no possibility of the reaction. That is, from here the chain reaction will be breaks, right? So to continue the chain reaction, we need to slow this fast moving neutron, right? So we are going to slow down this fast moving neutron. It has the energy that is of 2 mega electron volt. We need to slow down this energy to 0.025 electron volt. That means that we need to slow down this fast moving neutron, right? So with the help, right? So what that help is from the moderator. By using the moderator, we are going to slow down this fast moving neutron, right? So from Chadwick experiment, so he observed that in the elastic collision of the neutron with the hydrogen, right? So as already we know the elastic collision in class 11, right? So when neutron collides with the hydrogen, right? So when neutron collides with the hydrogen, then this neutron speed is almost decreasing. That means its speed is imported into the hydrogen, and hydrogen speed is imported into the neutron, right? So that is from elastic collision. So this is observed by the Chadwick. So Chadwick experiment, from the Chadwick experiment, so neutron is collided with the, that is bombarded with the hydrogen, that is elastic collision. The velocity in the neutron is transferred to the hydrogen, and the velocity in the hydrogen transferred to the neutron. So here the almost energy of the neutron is very less. That means speed of the neutron is very less and almost it comes to rest. it comes to rest, right? So here, when neutron bombarded with the hydrogen, then the energy is carried by the proton, right? So here, for that purpose, we using moderator as, that is, lighter nuclei, right? So because hydrogen is the lighter nuclei, its mass number is how much? 1. That is very less than that of the 30, right? So here when neutron bombarded with the hydrogen, so the speed of the speed of the neutron is almost less, and it is almost comes to rest, right? So by observing this experiment, that is from the elastic collision, which is done by the Chadwick, so here in the nuclear reactor we are using lighter nuclei as the moderators, right? So here hydrogen is the lighter nuclei, right? So here this lighter nuclei we are using as the moderator. That means here the moderator we are going to use, that is moderator lighter nuclei. So lighter nuclei which are containing the lighter nuclei, so that material we are using as the moderator. So in nuclear reactor we are using water, because water is formed by the hydrogen. Hydrogen is the lighter nuclei, right? So H2O, and heavy water. So heavy water is deuterium, that is D2O, right? So this one is the isotope of the hydrogen only, right? So next, and the third one is graphite. Hence, this core is covered with the graphite. So this graphite is used as a moderator, right? So what is the purpose of the moderator is? The purpose of the moderator is the fast moving neutron has to reduce its speed. That means it has to decrease its speed. Then for that purpose we are going to use the moderator, right? So in nuclear reactor we are using water or heavy water or graphite as a moderator, right? So this one is the third point, that is moderator. And the next one is coolant. So on the next one is coolant, right? So what is the purpose of the coolant? So here in the core, when the uranium is splits into the neutrons, then the energy is released. So heat energy is of the order of 10 to the power of 6 Kelvin. So this one is the heat energy released. So this heat energy is extracted by the coolant, right? So the purpose of the coolant is the heat energy is extracted by the coolant. Then this coolant is sent into the heat exchanger, or we call this one as the steam exchanger, right? So this coolant is very heat, that is hot coolant, right? So this coolant is sent into the heat exchanger and water is pumped in the heat exchanger. That means here the cold water is passing in the heat exchanger as the heat is flows on this tube, right? So here there is the exchange of heat into the cold. As the water absorbs the heat from the coolant, then water gets into the steam. That means it evaporates and the steam is produced. So that steam is used to turbines to rotate, right? So by the turbines is rotating, then we are generating the electricity, right? So this is the purpose of the coolant. So the purpose of the coolant is the heat which is generated in the core is to extract from the core and supplied to the heat exchanger. So in heat exchanger the water is supplied and that water gets absorbed by the coolant heat, and that water is gets evaporated, and that evaporated is converted into the steam, and that steam is used to rotate the turbines. So by rotating the turbines, the electricity is generated, right? So and the last one is control rods. Right? So here we have the control rod. So as already says the purpose of the control rods, right? So the purpose of the control rods is here the enormous number of the neutrons which are generating during bombarding with the bombarding with the. So if we observe the supplied neutron is how much? 1. So here the emitted neutrons is how much? That is 3. Right? So as already said, so this further it undergoes the reaction. So again here we getting 3, again here we are getting 3, again here we are getting 3. Right? So that means here the supplied neutron is 3 and the emitted neutrons is how much? That is 9. Right? So here the emitted neutron divided by the supplied neutron gives the ratio. That ratio is the multiplication factor. If the K value is greater than 1, that means the emitted neutron is greater than supplied neutron, right? So if you observe here, the emitted neutron is how much? 3. The supplied neutron is 1. That means 3 divided by 1 is 3, which is greater than 1, right? So this, when K is equals to 1, so this condition is super critical stage. So in this stage what happens means the reaction rate in the nuclear reactor is very high. That means reaction rate is high. This leads to explode. That means uncontrolled nuclear reaction takes place, because here the 3 neutrons again bombarded with the nucleus, again we are getting 9 neutrons, right? So this continuous goes on. So for that reason the K is greater than 1, so that stage we have the critical stage. So that one we call as super critical stage. In that the reaction rate is high and the chances of the explode is more, right? So next, when the neutron supplied is 1 and we need to observe these 2 neutrons, then the emitted neutron is how much? 1. That means the emitted neutron to the supplied neutron is how much? 1 is to 1. That means when K is equals to 1, that indicates that the critical stage, right? So here now observe, here we are supplying the 3 neutrons. So from these 3 neutrons we are observing almost 7 neutrons. That means the supplied neutron is how much? 3 and the emitted neutron is how much? 2, right? So this value is less, or so this one is 2, emitted neutrons is 2, supplied neutrons is 3. That is 2 divided by 3 almost equals to 0.8, 0.6, right? So this one is less than 1, right? So the third case is when K is less than 1, right? So this stage we call as subcritical stage, right? So for the controlled nuclear reaction we need to maintain either K is equals to 1 or K is less than 1 or K is equals to 1. So for that purpose we are using the control rods, right? So for controlled chain reaction we are using the control rods. So these control rods are absorb the neutrons which are present inside the core. So these are adjustable. So these control rods are we can put inside and we can take outside also, right? So when if we completely insert it, if it absorbs all the neutrons, then it will stop the further chain reaction. So for that how much quantity of the neutrons we need to observe means, so up to that we have to insert this nuclear, that is control rods, then we can take outside. So in emergency purpose, these control rods are also used to shut off the nuclear reactor. That means completely to close down the nuclear reactor. That means we need to stop this reaction, that is chain reaction. For that purpose also we are going to use this control rods, right? So in emergency cases, these control rods are also used to turn off the nuclear reaction or nuclear reactor also, right? So the control rods here we are going to use are cadmium and boron. Either any of these two, either cadmium or boron, we are going to use as control rods, because these are high power of absorption of the neutron. That's why we are using the cadmium or borons as the control rods, right? So this is about the nuclear reactor. So in nuclear reactor we have core. The first is core, the second one is the reflector, third one is moderator, fourth is the coolant, and the fifth one and the last is the control rods. So what is the purpose of using coolant? What is the purpose of using the reactor, that is reflector in the reactor, and what is the use of the control rods? So the possibility of asking for 1 mark, right? So we need to know all this, right? So this is about the nuclear reactor. This is about the nuclear fission, that is breaking or splitting of the heavy nucleus into lighter nucleus, and those nucleus are radioactive in nature, then it undergoes beta decay and it attains the stable nucleus by releasing the neutrons along with its energy, right? So this is about the nuclear fission and nuclear reactor. So in the next class we will discuss about nuclear fusion. So by this we are going to complete the chapter, that is nucleus, right? Thank you. Any doubts, Idana?